Hi, this is Stephen Barrow from Art Valley Community College. This is for CSIT 256, Computer Architecture and Assembly Language. And this is meant to be the chapter overview for Stallings Chapter 5. This is take 2 because take 1, I spent almost 4 minutes on the first 2 bullets we see on the screen. So there's going to be another video that's going to talk about those first 2 bullets in a lot more detail. But dynamic RAM is what's used for a primary memory. Static RAM is used for cache. And so, again, I'll have a video that will just go into some of the details of it, even showing a picture. Read-only memory. So either that same video or a different video will talk about read-only memory. But the intent of read-only memory is that whatever's there doesn't change. So if you ever look at a card inside of a computer, I'm talking like an expansion card, or even if you look at the motherboard itself, there are a number of chips on there. Well, what some of those chips hold would actually be the underlying programs. So it's the circuitry, what's controlling that device, is in this ROM, read-only memory chip. Sometimes it's also some data that it's using, so the data that's being used is on there as well. And so what another video will go through is we'll kind of step through the evolution that read-only memory has gone to, leading up to flash memory, which we'll talk more about the flash memory. One thing I do want to jump at a couple pictures, and again, there'll be another video that might go into more details. But in several places throughout the book, you'll see a schematic of a chip. So think of this as a top-down view of a chip. There are the pins that would actually go and plug into the board. And what this is showing is what each pin means. And what I want to point out are a couple things. All the A's, those are addresses. So for this being a memory chip, excuse me. Yeah, memory chip. For this being a memory chip, it's those lines for the address of what memory is needed. Those address lines, those A's, would be loaded in terms of the address of what it's looking for. The D's would be the data. So this particular one here has 11 bits for the address, 4 bits for the data. The V's are voltage. And that's one thing that's very important about is that if you take the wrong chip and stick it into a place where a chip goes, you may end up throwing voltage to something that shouldn't get voltage, and you can fry the chip. If we were in the classroom, I would tell you that story. I've done that before. Then the other things would be the control lines. So the other ones that are here would be the control lines. So again, thinking of a bus has data lines, address lines, and control lines. The D's would be the data lines. The A's would be the address lines, and everything but the V's would be the control lines, the V's being the voltage. On the right-hand side here, I decided that the right-hand side was getting into too much time, was making the video too long. So that's something in a later video we'll go into that. And 2 other pictures. I initially was going to have my overview and realize it's too long to go into an overview. One of the other things we're going to cover in the chapter is going to be the idea of a parity bit, P-A-R-I-T-Y, parity bit. And the idea is that a parity bit says something about the data bits that it accompanies. And we'll first take a look at a simple parity scheme, and then what we'll look at, like a simple parity scheme can only tell you there's an error, it can't tell you where it is. A more complex parity scheme can actually correct any errors that are detected. And what we'll do is we'll look at Hamming code as a way for, and basically it's 4 bits as overhead for 8 data bits that will allow us to then correct a bit. And part of the idea is if we're reading from memory, 12 bits, in terms of 8 of it, which is the data, and the 4 is the overhead. If there's a problem with a piece of the memory, that the Hamming code could then correct that. The latter part of the chapter, we'll take a look at RAM, which is synchronized with the CPU, so that there isn't any waiting for the CPU. It just makes the request, and at the next clock tick, it's available. Or in the, oh, that's a huge typo. That's enough.